All right, so today we're just going to go over kind of your fraction rules and your exponent rules, and then we're going to extend this into some grade 11 type stuff. So like I said, your fraction rules and your exponent rules are all kind of here. So the kind of the highlights from this are that when we are working with fractions, when we're adding and subtracting, we always need a common denominator. When we're multiplying and dividing, we don't need a common denominator. So with division, we always flip it into multiplication. So take the second fraction, flip, and change to multiplication. And then your exponent laws, when you are multiplying two things that have the same base, keep the base, add the exponents. Okay, power of a power, keep the base, multiply the exponents. Division of two things with the same base, keep the base, subtract the exponents. And then negative exponents can be written as 1 over that base to the positive exponent. Or you can switch it, whatever side of the numerator or denominator it's on, you can move it to the other one and make it positive. So if you see something with a negative exponent in a denominator, you can actually move it up to the numerator and make the exponent positive. So that's the negative exponent rule. We also have the exponent of 0 rule, so anything to the exponent of 0 is equal to 1. And that's because there's two ways that we can kind of prove this. If we have x divided by x, both to the exponent a, on the one hand, anything divided by itself is equal to 1. On the other hand, we can apply quotient rule, which says keep the base and subtract the exponents, which means we get x to the 0. So x to the 0 must equal 1. We've proven this kind of two ways. Okay, so we're going to do a couple little examples here just to kind of get ourselves back into it. A couple of these have variables. So we call these rational expressions if they have like fractions and variables in them. All right, so number 1, we need a common denominator between 6 and 8x. So preferably the lowest common denominator, right? So rather than multiplying 6 by 8, what are two things, like they need to both multiply to something, but ideally the lowest thing that they both multiply to. There, 24, and also each side needs an x. So to get to 24x, we need to multiply this guy by 3 on top and bottom. And on this side, we need to multiply by 4x. Okay, whatever you do to the bottom of a fraction, you also have to do to the top. All right, so we will get 4x times x, that's 4x squared, over 24x, plus 15 over 24x. And then you can merge these into one fraction. So keep the denominator and put the numerators together. Okay, one little thing that you should always check kind of at the end is if there's any common factors between your terms. If you reduce these individual fractions to start with, you won't have any common thing that can be common factored at the end to reduce with the denominator. But it's always good just to double check if you have multiple terms on top, see if any of those can be common factored. Kind of like we did with the quadratic formula, we common factored and reduced with the denominator. We'll check to see if we can do that. So yeah, this is our final answer. There's no common factor between 4x squared and 15. Okay, common denominator between 7, 6, oh actually first, this is actually what I was just talking about. Okay, notice in this individual fraction we have a 2y and a 6. I'm going to reduce that to 1 and 3. Okay, I can't reduce 8 and 3 and I can't reduce 3 and 7. What this does for us is it allows us to just make sure that our final answer will be fully simplified. Okay, so common denominator between 3 and 7. Lowest common denominator, ideally. Nina? 21. So this one needs to be multiplied by 7, same with the middle fraction. And this guy needs to be multiplied by 3. And then keep the denominator, put everything in the numerator together. Okay, if we wanted to, kind of like when we were using quadratic formula, you'll notice that there's a common 2 on top. 21 isn't going to reduce with 2 anyways, so you could leave it here, or if you want it in like fully simplified form, we could actually just common factor out that 2. What do we get there? 28. And we could write it like this. Again, this doesn't really help us reduce anything there, like it's already fully reduced regardless. So either one of these two answers would be fine. However, we do want to always check for those common factors just in case these things can be reduced. So it's always a good idea, just a common factor just in case you can kind of further reduce there. So maybe we'll just go with the common factoring method there. Okay, so there's some adding and subtracting with various fractions with variables in them. Now multiplying and dividing, we don't need common denominators for these. I actually really like when multiplying, and I think it's actually very helpful. Any top, when you have a multiplication between two fractions and like single terms like this, like there's no addition and subtraction, any top can actually be reduced with any bottom. So for instance, 2 and 10 here, I can actually reduce that to 1 and 5, just like I would reduce 2 over 10. So any top with any bottom. So I'm going to reduce that to 1 and 5. Okay, does anyone else see anything that can be reduced, any top with a bottom? Vanessa?
9, 3.
Yep. Okay, so right now we have x over 1 times 3 over 5x squared. Okay, there's something else that can be further reduced before we multiply. Declan?
Yes.
The x here, and I'm going to reduce that with 1x over here, so we'll just cross out the squared. And there's a 1 left over on top. Okay, multiply the numerators together. 1 times 3 is 3. And multiply the denominators together. 1 times 5x is 5x. And you will get a fraction that's fully reduced. Okay, this just makes it a little bit easier. Like, yes, you could multiply across on the top and multiply across on the bottom, like right away. But then you're going to be dealing with bigger numbers that you're going to have to reduce. So I personally think that it's much easier just to like reduce first, and then you'll get a fully reduced fraction at the end. Sophia?
So when you're like scratching out x squared and x, like how does that just form out?
So if I have 1x on top and 2x's on bottom, I can cancel out 1 from each. So what's left? 1x on bottom, right? Okay. With division, we are going to, before we cancel anything, we're going to flip and multiply the second fraction. So flipping that second fraction, change the division to multiplication. And then again, we can reduce any top with any bottom as long as there's multiplication in between my fractions and no like addition and subtraction happening. So what should we reduce here? Sure, we can reduce that to 1 and 2. Anything else? I think that's pretty much it, right? So we will multiply the tops together. 2 times 2 is 4. I have 3 x's and I'm multiplying it by another x. How many x's do I have on top? 4, that's good. And then 1 times 7. So we'll get over 7. And again, notice we get a fraction in fully simplified form by doing this cross-canceling step first. Any questions on any of those steps so far? We're okay? Can I scroll? Declan, are you okay?
Is it 4x to the 4?
4x to the 4, yeah. moving forward, let's work on a couple exponent rules here. Okay, so BEDMAS rules apply here, right? So we want to do brackets, exponents, then we'll do multiplication, division, and all of that good stuff. So the first thing that we need to do here is apply the exponent on this bracket. So exponent of an exponent means we do what with the exponents? Multiply. So x to the 6. Okay, in this step as well, I'm just going to take this negative exponent, and using the negative exponent rule, it says that I can move this term with the negative exponent up to the other side of the fraction and actually make that exponent positive. Okay, so that's the negative exponent rule. So I'm actually just going to move that y to the negative 2 up to the top, and then we can make the exponent positive there. Okay, you will know that your question or your equation is fully simplified when all coefficients are gathered, when all x's are gathered, and when all y's are gathered. Okay, so any 2 or 3 of the same variable, they all need to be combined into one. For instance, the coefficients, like I have a 3, a negative 1, and a 2. Those I can kind of multiply together. So I'm going to multiply that. I'll put negative 6 at the front. How many x's do I have on the top? I have 6 here. I don't have another one here. So we have 7. How many y's do we have on the top? We have 6. You can say y 6. Ainsley?
How come the x would be 7 and not 5, receiving negative x?
So the negative is just like a negative 1. So we multiplied 3, negative 1, and 2. The exponent on the x is actually a positive 1. So we have 6 plus 1, which gives us 7. Okay, now we need to reduce. Is that where you were going from there? So what would you reduce, Declan? Okay, so, and then what's left?
Then it would be x to the top, so it'd be 9.
So we have 7 x's on top, is what Declan's saying, and we have 5 on the bottom. We're going to cancel out 5 from each. So there's going to be 2 left on top. We'll be left with an x squared up here. Okay, in other words, we're using quotient rule. We're saying x to the exponent 7 minus 5, the top exponent minus the bottom exponent, right? Sophia, you look confused.
What happens to the negative 6?
I'm getting there.
Oh, okay.
We still have a y to the 6, and we also want to reduce 6 and 9 here. So what can we reduce out of both of those? 3. So I have 2 and 3. So we'll be left with a negative 2 and a 3 on the bottom. Okay, are we fully reduced here? Are all coefficients gathered? Are all x's gathered? Are all y's gathered? Yes, so we're done. Okay, are there any questions? Like, how did you get from this step to this step, Millie?
Can you go with this fraction from the top when you got a 6x7 to y6?
So for the 6 part, I'm doing 3 times negative 1 times 2. So all the coefficients multiply together. And then how many x's are on top? Well, I have 6 here, and I have x to the 1 here. So we keep the base, add the exponents, right? So I have a total of 7 x's on the top. And then same thing with your y's. You have 4 y's, and then 2 y's. So now we have 6 y's.
So let's do the y times 2y.
So this is, like when we have coefficients, like everything that's going on here is all multiplication, right? We're just multiplying it all together. So any coefficients that you have, those can all just be gathered. So the 2, the negative 1, and the 3, I gathered those all into this negative 6 here. Okay, it's just a number, it's a coefficient. We're not adding and subtracting them, so the number can just be multiplied like in front. Sophia?
At the top, when we have like an x2 back at 3, do we multiply the geometry square?
Do you multiply the what?
Do we multiply it, or do you, like, do you square root it?
Multiply what?
293.
We multiply them,
You
and we
just
get
multiply them,
6.
you don't deduct it.
Yeah. Any other questions? Okay. All right, so when we have a square root of a fraction, we can actually write this as the square root of the top over the square root of the bottom. Kind of like we do with multiplication. If I have multiplication under a root, I can write them as separate roots that are being multiplied. And I'm just going to take a little step here. This has a negative exponent, so we're going to take it and move it down into the denominator, and we can make the exponent positive. Okay, we are going to simplify our radicals here. So biggest perfect square inside of 8. 4, so we'll split that into 4 times 2. Square root of 49, that's just 7. Okay, and then I'm just going to square root the 4 part of this. And we're just going to reduce. So because we have multiplication in between, we can cancel any top with any bottom. So any suggestions as to what can be reduced here? Nair? Okay. 7 and 14 to 2 and 1. Anything else? Two and 4 to 1 and 2. Perfect. Okay, and then we're just going to multiply the tops. So we'll get 2 root 2 on top. That's what's left. And on the bottom, we have 2x to the 7. Are we fully simplified here?
No.
Well, the 2's can cancel, right? So root 2. Are we fully simplified now? Yeah, we're good.
Can't you just check? Usually you check if you go to
So because you have a variable, you can't really check that, but you could check. It's not going to tell you if it's fully simplified or not, but a really nice way that you can check your answer is choose an x value to enter into the original equation, like 2. And that should be equal to what you get for this if you enter in the same value for x. This is just a simplified version of this, right? So they should give you out, if you choose an x equals 2, let's say, in both of those, they should both give you out the same decimal value. Okay, I would stray away from choosing 0 or 1, just in case, but any other number is usually fine. Same thing here, choose an x and a y value, and sub that in and choose the same x and y value and see if you get the same decimal value for the first that you do for the last. Okay, that will at least tell you if they're equal or not, right? Because I'm saying this equals this, equals this, equals this. So at least that will tell you if it's equal. It's not going to tell you if it's fully simplified, but at least you know, like, if you've made a mistake somewhere along the way. Okay. So there's kind of your refresher on exponent rules and fraction rules. Restrictions. So there are things called restrictions, and essentially these things get produced if you have variables in your denominator, right, Danielle? So any variable in your denominator will produce a restriction. And here's the deal. We talked about real numbers last chapter. We know that things can't be divided by 0, right? If you try it in your calculator right now, you're going to get some kind of math error or something like that. I can't have something like 2 divided by 0, because really what I'm asking the calculator is, like, what times 0 equals 2? Well, what times 0 equals 2? Nothing, right? So we can't, like, when we think about division, we think of groups of, right? So if I split 6 marbles into 2 equal groups, then I'm going to have 3 marbles in each of my groups. Agreed? If I split 6 marbles up into 0 groups, that makes no sense, right? My 6 marbles at least need to be in 1 group, or they can be in 2 groups, or they can be in 3 groups of 2, or whatever, right? So we can't split 6 up into 0 equal groups. That doesn't make sense. So denominators can't be 0. That's a big fraction rule. And anytime we have variables in the denominator, we need to make sure that those variables don't end up being a value that could make the denominator equal to 0. So for instance, in number 7, for g at x, I need to make sure that this expression never equals 0. So I need to tell the reader that x can't be some kind of value. If x is being subtracted by 4, what value would cause x minus 4 to equal 0? 4, right? Because 4 minus 4 is 0. So x can be anything, but x cannot be 4, because then I will do 5 divided by 0, and I can't do that. Okay? So any variable in your denominator that could cause the denominator to equal 0, you need to make sure you restrict. Okay, you guys actually did functions like this in your first unit. They had asymptotes, and they're produced because we don't want the denominator to equal 0. That's what happens on a graph. Okay, sometimes it's going to be a little more challenging to see what's going on. So the best thing that you can do is factor the top and the bottom. So we're looking for 2 things that multiply to -8 and add to -2. -4 and 2 should work for that. Okay, and then for the bottom, multiplies to -12, adds to -1. Okay, so this is kind of like we're entering into some of the stuff that we're going to be doing in this unit. Anything at any time that's in your denominator, any variable that could cause that denominator to equal 0, it needs to be restricted. Now, in this case, I can actually cancel out this full group of x minus 4 with this full group of x minus 4. Those are common, right? So those can actually be canceled out. But even though this gets canceled out along the way, it still produces a restriction. So I still have to restrict that x, and I also want to restrict this x. So here's my final simplified answer. And with this, I'm going to also state restrictions on the variable. So let's start with this one. What would cause x plus 3 to equal 0? Okay, so x can't be -3. What would cause x minus 4 to equal 0? 4. Okay, so those are our restrictions. So I actually want to show you guys what these restrictions would produce on a graph. So I'm just going to pull up a graph really quick here for you. Yep. So the one that I canceled out, that one also has to be restricted. So any x that's in the denominator at any time that could cause it to be 0 needs to be restricted from the x minus 4 part. Okay, so take a look here on Desmos. So remind me again, what were our restrictions? Okay, so did you guys see what's going on at -3 here? What is this? It's a vertical asymptote. Now watch what happens. What's the other restriction? +4? Is that right? Watch what happens if I hover over +4 here. Might be hard for me to get. What do you guys see? What does it say? Undefined. So this is, remember those little hollow points that we looked at last chapter? Those were undefined points. Now, this is what happens if your restriction gets canceled out along the way. So see how that one got canceled out along the way? but it's still part of our final restriction. They both produce two different things. If you see, if you see a restriction in your final answer, like we can still see the x plus 3 there, that produces a vertical asymptote. Okay, so it's still visible in your final answer. It doesn't get canceled out along the way. Now this guy got canceled out along the way. We still need to restrict him, but it's not as crazy as a vertical asymptote. It just produces like a little undefined point. Kira, question?
Yeah, how come the restriction for 4 isn't negative 4? Because that's what we canceled.
So x minus 4, basically we don't want to put anything in for x that can cause x subtract 4 to equal 0. So if I put in 4 for x, 4 minus 4 equals 0, and that causes the whole bottom to equal 0. Does that answer your question?
Yeah.
Okay. Okay, so canceled out along the way, just an undefined point. You can still see it in the final answer, vertical asymptote. So is this guy an undefined point or a vertical asymptote? Say it louder. This is a vertical asymptote, right? It doesn't get canceled. We can still see it in the final answer. So this guy would be a vertical asymptote. Okay, so that's restrictions. So we actually didn't do restrictions up here, but some of these, because they have variables in the denominator, if we were doing those from here on out, we would make sure that we would put restrictions for any of those variables that are in the denominator. Okay. Last little section here, we're going to take a look at equivalent expressions. Sorry for the scrolling. Equivalent functions and expressions. So there's a couple ways that we can tell if two expressions are equivalent or are equal to one another, the same expression. I talked about that up here. So one of the ways that we can tell if this expression is actually in fact equal to this expression, what did we say? What did I suggest you do? Sub what in? Sub in the same number and check, right? So this doesn't like prove definitively like, yes, this is equal to this. But if I subbed in maybe like a couple different x's in here and then checked if they gave me the same decimal out, if I subbed in the same x in the final, I could be pretty confident that those expressions are equivalent, right? So that could be a way that I can check if two expressions are equivalent. This is essentially the way that you can check like basically every single answer in this unit. Okay, so this part is actually important going forward. We can simplify the expression and test and see like, oh, if I simplify and I gather like terms or I cancel or whatever, do I actually get this other expression? Or we can check the graphs and we can see if the graphs are equal. Okay, so I'm going to show you kind of the three methods here. So for the first one, I can test some x values. So let's say we test f at 0, f at 1, and f at 2, for instance. So I want to find what all of those are equal to. And I also want to find what g at 0, g at 1, and g at 2 are equal to. Okay, I think if we test 3 in there and we get the same answer, we can be pretty confident that those expressions are equivalent. Okay, so we're just going to sub in each of those x values. And I'll ask you guys to help me calculate these here. Okay, so what do we get for the first one? That would be 2 plus 1, so 3, I think. For the second one here, we get 0 plus 1, so 1. And then 2 plus 4, so 6. Correct me if I'm wrong, please. I'm just doing this quickly in my head. And then we get 0. 2 minus 1 is 1. And what do we get here? 8 minus 2 is 6. Did I calculate this right? I did. So, are these expressions equivalent?
No,
Why not, Declan?
because they're equivalent, they would have the same x value, or same y value.
Right, so although f at 1 and g at 1 are equal, and f at 2 and g at 2, they both give us 1 and 6, f at 0 is equal to 3, and g at 0 is equal to 0. So automatically, if f at 0 doesn't equal g at 0, we can say these expressions are not equivalent, as long as I've calculated correctly. Oh no, this is equal to 0. Guys, you're not catching me here. Right? 2 plus negative 2, that's 0. So, are these expressions equivalent? All right. So, I think we can probably confidently say if all three of those things are equal, the chances of those expressions not being equivalent and 3 different x values being the same in both of those is pretty slim. So I think for that one, we could say, therefore, these expressions are equivalent. Okay, we're also going to simplify the expression and check to see if we can simplify and maybe get to g at x with f at x. So I'm going to do that next. You guys can use, there's some space for you on the next page. So I'm just going to take f at x and I'm going to expand and simplify and see if we get an equation that's equal to g at x. So we're going to FOIL this first part here. Keep your brackets when you FOIL because the 2 has to go into everything there. We'll get x times x, which is x squared. X times negative 1, which is negative x. Negative 1 times x, which is negative x. And negative 1 times negative 1 is positive 1. Okay, also I can just drop the brackets on this second part here. Just going to gather up the negative x's inside the bracket there. And then we can bring in the 2. Okay, gather up your like terms here. And if the expressions are equivalent, when this is expanded and simplified, I would expect to get g at x. If they're not, and I don't get g at x, then there might be something wrong. Or they're just not equivalent, right? So here I get negative 4 plus 3x, so that's negative x, and 2 and negative 2 cancel. So is f at x equivalent to the g at x expression? Is this equal to g at x? Perfect. So that equals g at x, therefore we can say f at x must be equal to the equation g at x. Okay, so our findings from part 1 are reinforced again, right? Okay, and then the last thing that we can check is if I sub in the equation from f at x and the equation from g at x, their graphs should literally be the same. So if you go over to graphing technology here, we'll use this again. I'm going to enter in the f at x formula here, or equation rather. So there it is. And I'm going to enter in g at x. So 2x squared minus x. Oh, I must have done something wrong here. Oh, minus 2. There we go. Okay, so we can actually visibly see here that the graphs overlap one another. Okay, so that would be check using technology. Okay, so with the check for number 3, the graphs are the same. Okay, so that's kind of like 3 different ways that we can check if f at x is equal to g at x. Yeah, so you would have to have like a graphing calculator that you can use, or like you can check on Desmos, obviously not on a test, but a test you'd probably just utilize like the first or the second method. Yeah. Okay, any questions so far? Okay, we're going to test with one more to see if these 2 expressions are equivalent. So we actually did the simplification of this above. So if you noticed above, we factored the top. We got this. So this is actually the second part. And we factored the bottom. And we got this. And then I showed you guys we can cancel these out. Okay, so are these equations equivalent? At first glance, we would say absolutely they're equivalent. But what did we say were the restrictions for f at x? It was -3 and +4. What are the restrictions for g at x? So are these equations fully equivalent? The equation is the same, right, once we simplify, but f at x has an undefined point where g at x does not, okay? So these equations are equivalent everywhere except for when x equals 4, because f at x has an undefined point when x equals 4, but g at x is actually defined when x equals 4. So we could say, therefore, the equations are equivalent. Okay, g at 4 simply equals 4 plus 2 over 4 plus 3, so it equals 6 over 7. So g at 4 is defined, but f at 4 is undefined. Okay, a way that I can tell that my work is correct here, and this is probably actually one of the best ways that you can double check that this is in fact equivalent to this, with the exception of that little when x equals 4, is just test a couple x's. Okay, test when f is at 0, when f is at 1, and when f is at 2, and test when g is at 0, when g is at 1, and when g is at 2. Okay, if you take forward something in this unit, you should take forward this skill of checking, because this is going to tell you whether or not all of your answers are equivalent or not, right? So for the top, we'll get 0 squared minus 2 times 0 minus 8 over 0 squared minus 0 minus 12. Okay, so we're just going to enter each of these in to our equations. So let's just calculate these here. I think for the top we just end up with negative 8 over negative 12. So we can just reduce 4 out of both of those, or negative 4, and we'll get 2 over 3. Okay, for g at 0 we also get 2 over 3. Okay, top of f at 1 we're getting 1 minus 2 minus 8, so negative 9. And then 1 minus 1 minus 12, that's negative 12, which reduces to 3 over 4. Okay, same thing over here. We get 1 plus 2, that's 3. 1 plus 3 is 4. Okay, so far so good. These are equivalent. And then 4 minus 8, that's just negative 8. 4 minus 2 is 2, minus 12 is negative 10. So we're getting 4 over 5 here. And then same thing over here, we get 4 over 5. So we'll notice again that each of these has a match on each side. Okay, so we could be pretty confident. I mean, do we need to check 3 values necessarily? No. Especially like if on my first one I get that this isn't equal to this, then it's not equivalent, right? As long as I'm confident in my math work. So the only thing that this doesn't tell us is this, right? Because we didn't look to see if there were any restrictions. So if we were just testing numbers in here, we would assume that these equations are equivalent. But we know at x equals 4, there's a restriction in f at x. So we would have to kind of look at both of those things to decide whether those are equivalent or not. Okay, but we could probably make a pretty confident statement that these equations are equivalent, right? Lisa? I mean x cannot equal as far as a restriction. That's because any x in the denominator can't be 0, right? So the final thing that we would check here is, again, the graphs of both of these. So let's just take a look. I actually had this graphed before. Remind me what that equation was. Okay, so this is the one that we were looking at before. We're going to double check it with g at x. So that was x plus 3, was it, on top? X plus 2 on top. Okay, and we can visibly see that these two graphs are equivalent. So they're actually completely overlapping one another. So they must be equivalent expressions. The only difference is that when I look at 4 on g at x, it's actually defined. Okay, it actually has a value. But when I look at it on f at x, it has that undefined point that we talked about, right? It says undefined. So it's the only little tiny difference. Okay? Any questions? We're good? Okay.